Alright, welcome back. So, I'm going to start really quickly with an overview of Euler's method. Euler's method is a way we can use to solve differential equations. You know it from the formula as y new equals y previous plus a change in x times the slope. But what we're going to use it for is to make estimates of an integral. If I keep adding my previous y plus an xy, then we can eventually sketch out our entire curve. So this could be used when we know a formula for the derivative of an equation. So for instance, we know a formula for the velocity, but we don't know a formula for the integral of that equation. So we don't know a formula for the height of an object. So that could be something like if we've got an object that's in the air, we don't really know what the equation is for the air resistance. We can make estimates of the velocity, and then we can use this to get an estimate for what the height would be, maybe. So graphically, this is what we're doing. We're creating a tangent line at one point, and just extending that slope outwards for one more rise and run in order to create another point that we can use to estimate. So although this does introduce some error, with computers we could do this relatively quickly and to do step and step and step and step and step and step. Just a ton of steps all at once to get a decently accurate representation of the curve. And we could estimate the error if we needed to. Any questions on Euler's method?
No.
All right. Also going to look at separable differential equations really quick. So separable differential equations are differential equations. That's an equation for dy over dx or dy over dt or whatever our x-axis is, where we can separate our variables such that all variables of one type are on the left side and all variables of the other type are on the right side, in which case we could integrate without having some sort of multivariable calculus. So, for example, here I've got this derivative is 3e to the x over y squared. I've also got a point given, which means we'll be able to solve for a particular solution instead of just a general solution. So the way we can do this is, for our first step, separate all of our variables by moving all of our terms that have y's in them over to the left. Okay, hello again. Can you hear me?
Hello. I don't know if it was me, I think, but I wasn't able. I think I was a problem with my connection.
Yeah, no problem. So, pull us back up. Okay, looks like I've got Nikita with us now. Hello. Alright, so we separate our variables, move all the y's to one side, move all the x's to the other, and then we can integrate normally. So this will become from y squared to y cubed over 3 plus c, and then from 3e to the x and to 3e to the x again, since 3 is a constant, and the integral of e to the x is e to the x. Okay, that leaves us with plus c's on both sides, but because they're both constants we have not solved for yet, we can combine those. So c minus c will not give us 0, c minus c will still be some constant since they're not necessarily the same constant value. Okay, then I can solve for y, and that gives us a general solution. But because we are given a point, we know when x is -1, y is all of this. We could potentially plug that in order to solve for our particular solution. Hello, Kelly. So if I wanted to plug that in, I can substitute for y, substitute for x, and we should be able to solve for c, and then plug that back into our general solution in order to get our particular solution. Okay, any questions on separable differential equations? Alright. So I'm going to jump into an FRQ and we'll just bounce around. So starting with this one from 98. I've got a differential equation given by xy over 2. The first thing they want us to do is to sketch a slope field of this differential equation at the 9 points that they've measured here with dots, that they've indicated here with dots. So if I've got xy over 2, what are the easiest slopes to draw, do you think? So I'm going to start with Kyle.
The easy would be the one on the points located on the y-axis.
Okay, the one's on the y-axis. So and when x is 0, what's the slope?
Would it be undefined because it's 0 over 2, or will it be a straight line? I think it's just a straight line.
Okay, the slope would be 0, so in that case, we would have a straight horizontal line. So our slopes will look like this. Okay, over to Kelly. At 1, 1, what's our slope?
1/2. So
1/2.
Yeah.
Okay, 1/2. So it's rise over run. So 1, 1, 2. I should be pointing towards that line. At 1, 2, my slope would be 1. So I'm going to be pointing towards this point. At 1, 3, my slope would be 3 over 2. So it should be a little bit sharper. So this is down 3 over 2. I'm going to be pointing towards this line over here. Something like that. On the other side will be negative, but our y values are the same. So this is going to be the exact same slopes, just negative instead of positive. Any questions on anything that we did for A? Okay.
No.
For part B, so y equals f of x is a particular solution to the given differential equation, which I'm going to copy down here. So our given differential equation was dy over dx is equal to xy over 2, just so I can zoom in without having to see that whole graph. So f of x is the solution to this with the initial condition when x is 0, y is 3. I want to use Euler's method starting at x is 0 with a step size of 0.1 to estimate f of 0.2 and show the work that leads to our answer. Okay, starting with Kyle, what's the formula for Euler's method?
Y new is equal to y previous plus delta x dy over dx.
Okay, so our new y value after one step size is going to be my y value at 0.1. So that's y new. Equals our previous y value. So that's our y value at 0. Plus our change in x. We're stepping at 0.1 times our slope. So at my previous x and y value, what was my slope?
X 0 and 3.
Okay, 0 and 3, so that's 0 times 3 over 2 is 0. So I'm going to end up still at the same y value that we were at 0. Or our estimate for y at 0.1 is how much?
0, so that would be 0. So just 3? Y is equal to y 0.1 is equal to 3.
Okay, just 3 again. Okay, over to Kelly for our next step. Our next step will give us y at what x value?
0.2.
0.2. Okay, so that's going to be my previous y value, which was y at 0.1.
3.
Yep, 3.
Yeah.
Plus what?
Plus 0.1 multiplied by 0.1 times 3 over 2.
Perfect. So that's my previous x and y value. I think this might be easier to do as fractions, maybe. So 0.1 is 1/10. So this is 1 over 10 times 1 over 10 times 3 over 2. So what is 1 over 10 times 1 over 10 times 3 over 2?
3 3 over 200.
Okay, so I got 3 over 200. If I get a common denominator, what is 3 in terms of 200?
Oh, 600.
Okay, so my final answer should be
603 over 200.
perfect. All right, any questions on part B?
No.
So with that then, part C, we've got a particular solution to the given differential equation. Find the particular solution to the given differential equation with the initial condition f0 is 3, and then use our solution to find f at 0.2. So we'll see how good our estimate was with Euler's method by getting the actual value in part C. I'm going to change colors. Part C. Okay, dy over dx is xy over 2, and we were given that y at 0 equals 3. Alright, Kyle, back to you. How do I solve for y in this equation?
We would first separate all the variables into.
Okay.
Put the y
So-
on one side and x on the other.
Right, separate the variables. That means move the y's to one side, move the x's to the other. So this will be dy over y is equal to
X over 2 dx.
x over 2 times dx. Okay, then we can integrate normally. So I'm going to jump over to Kelly. Kelly, if I integrate this on both sides, what's going to happen? Oh, dy over y.
Natural log of y plus c equals x squared over 4 plus c.
Okay, perfect. When I combine these plus c's, they will not cancel. That's because they're not necessarily the same constant value since they came from separate integrals. So I'm going to move this plus c over to the left side, and I'll still end up with a plus c on the right side. Okay, next step. Kyle?
So solving for. Are we solving for y?
Yes.
Okay. So we do e, I believe.
Okay, raise
E
both
on both
sides to a
sides.
base of e. Perfect. So if I raise both sides to a
Oh.
base of e, what's the left side going to become?
Y.
Y. So y equals e to the x
E
squared over 4 plus
power.
c. Kelly, how can I rewrite this part?
Y equal e to the x squared over 4 plus c. Like, yeah, not as an exponent.
If I'm multiplying two numbers with the same base together, then I can add the exponents. 2 to the 4th times 2 to the 6th is 2 to the 10th.
So multiply by c.
Multiplied by c, okay. So this would really be e to the x squared over 4 times e to the c power. And e to the c power is c. This is the same thing as c e to the x squared over 4. Okay, so this is my this is my general solution, but we still need to find our particular solution. We know that when x is 0, y is 3. So I'm going to mark this. If y equals c e to the x squared over 4, but y at 0 equals 3, and then we can substitute and solve for c. Whose turn is it? This is Kyle next. if I plug in x equals 0 and y is 3, what's going to happen? Or what should I write for my next line?
It would be y equals 0 is equal to 3. 3 is equal to CE x squared over 4.
What is x?
Oh, 0?
Okay, so this will be 3e to the 0 power. What is anything raised to the 0 power?
1.
1. Okay, so then 3 equals c times 1, or c. So then we can substitute in. If 3 equals c, then y equals 3 times e to the x squared over 4 should give us any point. Okay, and they asked us to use that particular solution to estimate f of 0.2. So Kelly, last step. What is y at 0.2? Or what do we need to do?
3e to the 0.04 over 4.
Okay, 0.04 over 4. Well, what is 0.04 divided by 4?
Um, um, 0.01.
0.01. So this is going to be 3e to the 0.01. I think that's as far as I'd go without a calculator. I might rewrite this as 1 over 100, but if we had a calculator, then this will end up being around 3.030-ish, I think.
Yeah.
Looking at notes from last time, but I'll do that again just to double check. Yes. Alright, so zooming back out for the whole thing. Any questions on this one with the separable differential equations?
No.
Alright. So I think I'm going to go back and we're going to take a look at logistic equations really quick. I did do this in day 2 with Andrew, but I don't think either of you were there. So we'll do a quick review of logistics, which might be new for the BC class, I think. I don't think I did logistics. And then we'll take a look at one more that includes logistics. And if we do as well as we did last time, I might just call it there because we're doing really well. Alright. So here I've got a special type of function we call a logistic equation. Logistic equations are what we use to measure populations in the real world. So you might remember from middle school, if you took a biology class, we would talk about exponential growth for things like bacteria in a petri dish. So if you had a strand of E. coli in a petri dish, it would continue to divide itself. So you would be increasing according to this formula. A equals PERT, where P is the population of E. coli cells that you start with. R is your rate that you're increasing. In this case, we're increasing by 100% every time that you split, and then T is how many times that you've split. And that would tell you what your population is at the moment. The problem with this model is that in the real world, if E. coli were to continue to split this way forever, then the entire world would be nothing but E. coli cells relatively fast. Thankfully, in the real world there's limits in terms of size or space constraints on a population. or food, water, available resources, that we can't continue to multiply exponentially for our populations forever. So in the real world, the graph of E. coli cells would actually look something like this. So if this is our population on the y-axis, at any time, there will be some upper limit to our population. So our population of E. coli cells will start from some value, so we'll say 1 cell. We'll keep dividing up until the point where it reaches half of its environmental capacity or carrying capacity. And then after that, our graph changes and starts to look almost like a logistic equation as we approach that upper limit. It is easier to define this type of graph in terms of the slope rather than in terms of the actual population. So here I've got two different examples for how I could define this logistic growth of the E. coli cells, which are given in terms of the first derivative. So my change in population over time is equal to some constant k times our population right now times 1 minus population over our carrying capacity, which is, again, the maximum amount of E. coli that the Petri dish can support. And if you look at this, when our population is 0, then our slope is 0. And towards this left side of the graph, we can see that's true. As the slope becomes 0, our population approaches 0. But as our population approaches our upper limit, if p approaches L, then this will be 1 minus L over L, or 1 minus 1 is also 0. So if p goes to L, then dp over dt is also 0, which you can see is happening here as well. If our population approaches our upper limit, then the slope of our population also becomes 0. Any questions on what's going on with our differential equation? Alright, I could also write my differential equation like this. Again, if p is 0, the whole slope is 0. And if p is L, then the whole slope is 0 as well. If you're in a situation where you actually start with too much population, so we release 100 elephants on a small island that can only support 4 elephants, then our population will do the exact same curve from wherever your population started until it approaches our upper limit. So I still got a point where we're concave down up to a point where we're concave up, and I'm approaching that limit as we go towards infinity for time. Our fastest growth rate in this case, for real-world population growth, is when we're at half of our environmental carrying capacity. So at half of our upper limit, we'll be growing as fast as possible, which just means dp over dt will be the largest positive value possible. We can see this because if I wanted to maximize something, we could derive it, set it equal to 0, solve for our input. So if I take this equation here on the right, if I want to maximize my slope, the change in population over time, or our growth rate, then I can derive this equation with product rule. So the derivative of kp would be k, our constant, times L minus p, plus the derivative of kp is p, times the derivative of L minus p is negative 1. So that's k times negative p. And when we combine those, so k times L is kl, k times negative p is negative kp. So I've got kl minus 2kp. So our second derivative will be 0, which will be our maximum of dp over dt, when either k is 0, k is a constant, so we can't change the value, so that's not going to happen. But it could also happen whenever p is 1/2 of L, which would make this equal to 0 as well. Okay, last thing to show is if I wanted to create an equation for p, and then I could solve this using a separable differential equation. So taking one of these logistic growth equations, dp over p dt equals this one, p over 500 times 10 minus p. So in this case, our carrying capacity, the limit the environment can support, is 10, and our units are billions of rabbits. So this environment can support 10 billion rabbits. At half of that, so at 5 billion rabbits, our rabbits would be growing as fast as possible. Okay, so to solve this, to get a new equation for the population of rabbits at any time, we could create a separable differential equation. So I'm going to move all my p terms to the left and all my t terms to the right. So divide by p, divide by 10 minus p on both sides, and then multiply by dt on both sides, and I'll get this equation. From here, though, I'm going to have to use some partial fraction decomposition before I can integrate in order to break that left term apart. So with partial fraction decomp, there should be two fractions, something over p and something over 10 minus p, that I could combine in order to get our common denominator. So with that, a times 10 minus p plus bp should be equal to 1. So that would give us two fractions of the common denominator, and we could add straight across. Okay, so that gives us this equation, a times 10 minus p plus bp equals 1. And we can plug in any population you want, and these are constants, so their constants should not change value. So if I plug in p equals 10 right now, then I'll have a times 0 equals 10b, and b would be 1/10. If I plug in p equals 0, then I'll have b times 0 is 0, a times 10 is 10, so a is 1/10 as well. You can plug in those constants, then integrate normally. So when I integrate, both of these are really 1 over u. So I should get the natural log of u times divided by u prime. So I end up with this. Any questions up until this step?
Where did the 1 come from? Like when we do partial fraction decomposition?
Where did, sorry, you broke up the second part. So where did what come from when we did partial fraction decomposition?
Yeah.
I'm sorry, I didn't understand the question. What did you say?
Where did 1, like the 1 over p times 10
Oh, I see.
times, yeah.
On top we had dp.
Yeah.
So this is the same thing as 1 times dp, right?
Oh, okay.
Okay, good question. Anything else? Kyle, you okay?
At the moment, I think so.
At the moment you feel okay, alright.
Yeah, if I have any questions, I think I'll just ask later on.
Okay, cool. So, from this step then, I'm going to multiply everything by 10 in order to get rid of our fractions. When I multiply the c by 10, that stays c. I can raise both sides to a base of e. I can multiply e to the t over 50 times e to the c power, which is the same thing as c e to the t over 50. Then I'll multiply both sides by 10 minus p in order to get p equals c e to the t over 50 times 10 minus p. I'll distribute c e to the t over 50 into both terms. So 1, 2. That gives me 10 c e to the t over 50 minus p c e to the t over 50. I'm going to add that to the other side so that I can factor out my p's. If I factor out my p's from both of those terms, then I'll end up with p times 1 plus c e to the t over 50, and I can divide by everything that's not p in order to solve for p. Any questions on how we got here? Okay, Kyle.
For when we integrate both sides, so we ln p and ln 10 minus p, they subtract, since it's logarithm they divide. But is the 1/10 already distributed to the other side, to t over 500? Like, do we divide what
Okay, so in
from both
this
sides?
term, in this line, not yet. So I pulled out the 1 over 10 because that was a constant from both of my integrals. I can also pull out the 1 over 500 on this side. So when I integrate dt, I get t. So this will be t times 1 over 500 is what happened on the right side. On the left sides, when I integrate 1 over p, I'll get natural log p. When I integrate 1 over 10 minus p, I'll get the natural log of 10 minus p divided by negative 1. So I'd have to divide by u prime. So that's why this is negative instead of positive.
Okay.
Okay, after that step, I multiplied both sides by 10.
Oh,
So what that does is that gets rid of the 1/10, gets rid of 10 from the bottom of this one, and because 10 times c is still c, this one stays c. Okay, but I also used some properties of logarithms to combine what was left here. So I'd be left with ln p minus ln 10 minus p. If I'm subtracting logarithms of the same base, then I can combine those into one logarithm by dividing. So this is quotient property of logarithms. Oh. What did I just do? There we go. Log base a of b over c. Does that answer your question? I got a thumbs up. I'm going to say that's okay. Alright. So, from here, I could plug in our given, which was when t is 10, our population is 1/2 to solve for c. Oh, move forward. Oh, I guess that's where I stopped. I could plug in t equals 10, p equals 1/2, and solve for c from here, and I would get a general form. I did do it last time. I think I'm not going to do it now, because we just did one of those in the other problem. But the hard part here is really the partial fraction decomp from a logistic equation. Any questions on what we did? Okay, I think I've taken questions from both. So going once, going twice, and we'll stop there. Alright, so we'll do an FRQ to see what this looks like on your BC exam. So here I've got a logistic equation. dy over dt equals y over 8 times 6 minus y. Y equals ft is the particular solution to this differential equation. When t is 0, y is 8. Okay, for the first part, the slope field of the differential equation is given below. They want us to sketch the possible solution curves that go through the points 3, 2, and then a separate curve for the one that goes through the point 0, 8. Okay, they've marked those here, but it's a little bit hard to see in black and white, so I'm going to go ahead and mark over these in red so it's a little bit easier to see. Okay, over to Kelly. I want to sketch the solution curves that pass through those points. Can you tell me what you would do?
I don't know.
Not sure. Kyle, do you know what to do?
Do we sketch like do we follow the slope line until it reaches the I want to say the straight line near 6?
Right, so we're just going to follow these slope lines up until here. So I've got something like this, and then we'll do the same thing on top. Alright, for this bottom part of the slope line, we should be getting closer and closer to 0 as we go. I'm going to redraw this really quick. So getting closer and closer to our population of 0. And I know that's true because here at our logistic equation, if I plug in y equals 0, the slope is 0. If I plug in y equals 6, the slope is also 0. Any questions on our sketch?
No.
All right. Kelly, I'm going to take you for part B then. For part B, we
Okay.
are using Euler's method with t equals 0 and 2 steps of equal size to estimate f of 1. So first, what's our general form for Euler's method again?
Y new equal y previous plus delta x dy over dx.
All right, awesome. So for this one, starting at t equals 0, we want to estimate f1 with 2 equal steps. So what should our first step look like?
Y of 0.5 equals y of 0 plus 0.5 multiplied by
We said starting at t
y,
equals 0. Okay.
yeah, well, y over 8 times 6 minus y,
Okay, y over 8 times 6 minus y. What's our y value?
0.
That's
It's 8.
8. Okay, so this will be 8 over 8 times 6 minus 8. Okay, what is 8 over 8 times 6 minus 8?
Negative 2.
Okay, so this is negative 2 times 1/2. And then our y at 0, which was 8. So I've got 8 plus 1/2 times negative 2. What is 8 plus 1/2 times negative 2?
Oh, 7.
7. Okay. Jumping over to Kyle, we've got one more step left. So if I want to find y at 1, what do I need to do?
Put the y1 is equal to, so that y previous, so y of 0.5 plus 0 plus 0.5. 0.5,
Okay, y at 0.5 for our previous one, plus change next.
so 0.5
0.5, I'm going to write this fraction. Okay, then
dy over dx, so y over 8. So we're in this case 7. So 7
perfect.
over 8 times 6 minus 7.
Awesome. Okay, so I'm going to substitute 7 again. So this is going to be 1/2 times, what is 7 over 8 times 6 minus 7?
6 minus 7 is equal to negative 1. Negative 7 over 8.
Okay, so I've got negative 7 over 8 times 1/2 is negative 7/16. So right now I've got negative 7 over 16. What is 7 times 16 so that we can get our common denominator here?
7 times 16, 112.
Okay, 112. So I've got 112 minus 7 over 16 for our final answer.
So 105.
105 over 16. Looks good. Did they ask us to do anything else? Nope, that's it. Okay, any questions on part B before I jump?
No.
All right. So that brings us back to Kelly, I think. Kelly, they want us to use a Taylor series to make our estimate instead. So we want a second degree Taylor polynomial about t equals 0. What do I need to do to get our second degree Taylor polynomial? Change colors here.
I forgot.
Do you remember from the formula sheet what our equation for a Taylor series is?
Um, uh,
So I'm going to start from n equals 0, go to infinity. Oh, sorry, cut you off.
is it f of x?
Really close. It's the nth derivative at x. Okay, can you keep going from there?
Okay. X of n minus 1. Oh, and just n, right? Over n. Factorial.
Factorial, okay. So this is really an equation of a Maclaurin series that we created. If I wanted this to be a Taylor series, then I would change these x's to be x minus a's, but this will work for now, because we are centered at 0, and a Maclaurin series... I can't write on this, sorry, but Maclaurin series is a Taylor series centered at 0. So with that, we need to know what the 0th derivative, so that's just the y value, is at 0 for our first term. We need a second degree, so we'll need to be able to derive this one more time and then get the second derivative in order to do all of our terms. So Kelly, back to you for the first term. N is 0. So this would be, I need f to the 0 at 0 times x to the 0 over 0 factorial plus f to the 1 at 0, x to the first power over 1 plus f prime prime at 0, x squared over 2. And that would be a second degree Taylor polynomial. So now we just need to fill in the blanks.
Okay.
Alright, so if we don't derive, but we plug in 0, then what's our y value?
8.
8. So this should be 8 times x to the 0 power. What's x to the 0 power?
1.
1. So this is 8 times 1 over, what's 0 factorial?
1.
1. Okay, so this first term is just 8. Okay,
Yeah.
plus the derivative when x is 0. What's the equation when for the derivative?
The dy over dt.
dy over dt, okay? When x is 0, what is y?
Y is 8.
8. Okay, so we need to plug in y equals 8 into that derivative, and we should get a number.
Negative 2.
Negative 2. Okay, so this is... I'm going to change this plus and just subtract. So this is minus 2x to the first power over 1 is minus 2x.
Yeah.
Last one. Let's see. If I derive this, I'll get my second derivative of y in terms of time. What's going to happen?
Um, 1 over 8. times.
Okay, I've got options here. I can either distribute before you derive, and then we can derive with power rule, or I can leave this separate, and then we'll have to derive this with product rule. What do you prefer?
Distribute.
Okay, let's distribute
That's-
first.
yeah.
Okay, so this will be y over 8 times 6 is what?
6y over 8
Okay, 3y over 4 minus...
minus y squared over 8.
Okay, if I derive, what's going to happen?
3 over 4
Chain rule?
right, dy over dt
Okay,
minus y over 4 times dy over dt.
dy over dt, perfect. Okay, so right now, our y is 8 and our dy over dt is negative 2. So the second derivative of y when t is 0 is equal to 3/4 times what?
Negative 2 minus 2 multiplied by negative 2.
Okay. What's 3/4 times negative 2?
Negative 3 over 2 plus 4.
Plus 4. I'm going to write plus 8 over 2. So our final answer is
5 over 2.
5 over 2. All right. So 5 over 2 is our second derivative, and I can plug that in. So this will be plus 5 over 2 times x squared divided by 2. What should I write?
5x squared over 4.
Perfect. Okay, we've got a second degree Taylor polynomial of our function. Oh, our input's t, not x, so I need to change all of these x's to t's. My bad. T, T. T, T, T. T, T. Alright, awesome. Last step of this. I want to use our estimate to approximate f at 1. So if I plug in 1, what's going to happen? And then we're done.
8 minus 2 plus 5 over 4.
Okay, so let's get common denominators and then we can add straight across. So what is 8 in terms of 4?
32
Okay, 32/4 minus...
minus 8 over 4.
plus
Plus
5/4. Okay. So f at 1 is roughly how much?
29 over 4.
29/4. Alright, so we've got two estimates. Kyle's estimate using Euler's method, Kelly's estimate using Taylor series. Can I think both of you have had calculators for previous questions, so Kelly, if you can give me what 29 over 4 is as a decimal, and then Kyle, if you can give me 105 over 16 as a decimal, we'll see how close we were.
For 105 over 16, it's 6.5625.
5625.
Oh,
Uh,
6.6.
Okay. 6.5625. Kelly, how
Yes.
much is 29/4?
7.25.
7.25, okay. Alright, so for the last one, I want to know what the range of f is when t is greater than or equal to 0. And what does range mean first?
What's the lowest and highest possible outcome we can get?
Okay, so that's what's the lowest and the highest possible y value. Okay, so right now, taking a look at our estimates, our limit, so our carrying capacity that the environment can support, is currently 6, right? But our estimates are above 6. So that means we're actually looking at this red function that we have up here on top. So if t is greater than or equal to 0, what should the range be? So what y values are possible?
7, between 6 and 7. Between 6 and 8,
Between
but
6
not
and
6.
Okay, between 6 and 8. Perfect. The range is 6 is less than y is less than... okay, we're not going to hit 6, but I don't know if you can see. Let me zoom in here. This says t is greater than or equal to 0. So if t is equal to 0, we know we're at 8 exactly. So I am going to throw an equal sign here. So the range is 6 is less than y is less than or equal to 8. For t is greater than or equal to 0. And that was part D. I should have done that in a different color. But hopefully everyone will understand after the fact. Any questions for the last free response?
No.
Alright. So I'm going to end here, I think, because you guys both did really well on both of those. If you have questions about the homework, then I can stay and answer any questions you've got about the homework. And if not, I guess I'll see you guys... Actually, don't know if Monday's an A day or a B day, but I'll see you guys next week.
I think we have our class on Tuesday, I believe.
We've got class on... Wait, we're not coming back Monday? I thought we were back on Monday.
Oh no, I mean our calculus class will be on Tuesday.
Ah, okay. Sorry. Alright, so do either of you had questions about the homework, or do you want to end here?
I'm fine with the homework.
Okay. Alright, thank you guys so much for coming then.